Basic things and some definition oriented stuff in linear algebra. So from this part of the course, we start doing some theoretical things which students might have not encountered before. So it is very important to focus on the definitions that we cover here. So first, let us begin with vector subspaces. What is this vector subspace? Now, vector subspaces has a very simple definition. First, let me just write down the definition. A subspace, say V of Rn, is called a vector subspace if it obeys some criteria. So what are these criteria? V must be non-empty. That means there must be at least one element inside V. What's the second criteria? V must be closed under scalar multiplication. What does this mean? We'll take an example and then it will be clear. And the third and the last criteria is that V must be closed under vector addition. So now let's just go over this definition once. So a subspace V is a certain subspace of Rn. So what do we mean by Rn here? It is just nothing but a column vector consisting of n rows and one column. So this is Rn essentially, and R is the space of all real numbers. So this is Rn essentially. Now moving on to the other part of the definition, it is called a vector subspace. V must be non-empty. So this is quite simple. V must have at least one element. V must be closed under scalar multiplication and closed under vector addition. What does this mean? Let us just take an example for it to be clear. For example, let me say V is a vector subspace consisting of points x, y, z. This is a vector representation x, y, z such that x plus 3y plus z is equals to 0. Now let us check if is V a vector subspace. Is V a vector subspace? How do we analyze that? First, is V non-empty? No. Yes, V is actually non-empty since 0, 0, 0 is contained inside V. So hence first this rule is satisfied. Second, if any point, say we have a point x1, y1, z1 that's contained in V, and x2, y2 and z2, say that's also contained in V, then is the point x1 plus x2, y1 plus y2 and z1 plus z2 also contained in V? This is actually the third rule. This is closed under vector addition. So you can see that this is obviously true, because if x1 plus 3y1 plus z1 is 0 according to this first equation, then according to the second equation, x2 plus 3y2 plus z2 is 0. And if we add both of these equations, we will get x1 plus x2 plus 3y1 plus y2 plus z1 plus z2 is also 0, which means that this statement is actually true. So this is also closed under vector addition. Now what is scalar multiplication? Scalar multiplication is nothing but just multiplying the vector by a scalar. So if x1, y1, z1 belongs to V, then lambda x1, lambda y1, lambda z1 also belongs in V. Then lambda is any real scale. Now there are four major examples of vector subspaces. What do I mean by that? What do I mean by four major examples? What I'm trying to say is that except and apart from these four, there is no other format of a vector subspace. What are these four? First, plane passing through origin. What's the second? The second is line passing through origin. What's the third? R3, the whole of R3 itself is a vector subspace. Mind you, we are only generally talking about vector subspaces in R3. So these are four major vector subspaces in R3 actually. And what is the last? The singleton 0, 0, 0, this vector is a vector subspace in R3. This is very important to understand. Apart from these four, there are no other vector subspaces that we know of. So these are critical examples of vector subspaces, and any vector subspace that you've been given can be considered to be a subcase or modification of these four. So this is very important. Any other vector subspace, let me just write this down. Any other vector subspace is equivalent to any one of the above 4. This is very important. As we did in the example above, plane is certainly, it's clear why I'm saying that plane is a vector subspace. Similarly, if you write a line, let me just take an example of a line, x minus x1 upon, say, a is equals to y minus y1 upon b is equals to z minus z1 upon c is equals to, say, some constant k. So this is the equation of a line actually, but it's not passing through origin. This is equation of a line. It's not passing through origin. So for a line passing through the origin, we have x by a is equals to y by b is equals to z by c is equals to 0. We have this equation is equals to 0. So this is equation of line passing through origin. So this is an example of vector subspace. How do we check that it's an example of a vector subspace? Just check the rules number 1, 2 and 3. So those will prove that this is a vector subspace. And similarly for 3 and 4. This is also 2, 3 and 4 are vector subspaces as well. So it's a very important concept.